Right now we're in section 2.6, the Cauchy criterion. We already discussed the notion of convergence of a sequence in the past, and now we'll introduce the concept of a Cauchy sequence. This is the content of definition 2.6.1 in the book. So a sequence AN is called a Cauchy sequence. It's called Cauchy if for every epsilon greater than 0 there exists an n in n such that for all n m greater than or equal to n, one has that the absolute value of an minus am is less than epsilon. So this is a notion that does not mention a limit at all, but the two things are, a convergent sequence and a Cauchy sequence are very much related. In the case of R, a Cauchy sequence will be convergent, and of course, something that we're going to see pretty soon is that every convergent sequence is in fact a Cauchy sequence. So because this condition here tells you that the elements in the sequence and the tail are approaching each other, so they're trapped near a neighborhood of other elements in the tail. So for big enough n, all the elements in the sequence are going to be close to the element a sub n, sub capital N. Of course, a sub capital N is not going to be the limit. This is not true for a convergent sequence. It just tells you that, roughly speaking, these elements are getting closer to each other, and so you tend to think that there should be a limit. They're approaching to all the elements. This is only true when we have something like the axiom of completeness, or what's equivalent in this case, the nested interval property, which you can introduce in your theory as an axiom, or also the least upper bound property. Okay, but as it is, so we do have that, but it need not be the case that if you define or you try to do topology, so you try to do topology in any set, you will have this property, the Cauchy sequences. Even if you have a general metric space, you have a Cauchy sequence, it will be convergent. Just think of Q. So the rational numbers, in the rational numbers, as we will see later on, it will be very easy to construct sequences that are going to be Cauchy but not convergent in Q, because they will actually be convergent to an element in R. So if you pick an irrational number, you know that the irrational numbers are dense, so you can always approach irrational numbers, so that will mean that the sequence is convergent in R. We'll see any convergent sequence in R is going to be Cauchy. Therefore, the sequence is going to be Cauchy, living in Q. However, we will not have a limit in Q. So we need the axiom of completeness, or the least upper bound property. But fortunately for R, that is the case. So the R has the least upper bound property. And so this is what we're going to take advantage of. So for first important result that touches upon the relationship between a Cauchy sequence and a convergent sequence is the theorem 2.6.2. So that says that every convergence sequence sorry, every convergence sequence is a Cauchy sequence. For the proof, this is just an application of the triangle inequality and the definition. You know, I mean, being a sequence being, a convergence sequence satisfies there is an L such that for all epsilon greater than 0, and well, there exists an N, a capital N, and you know the rest. So we're going to take advantage of that to try to prove something that looks kind of similar here. It's just like as in previous applications, we're going to use a different epsilon for the other statement we want to take advantage of. So let's start by looking at, giving ourselves an epsilon, arbitrary epsilon greater than 0. Remember what I told you, whenever you have to prove a property like this, so that for every epsilon greater than 0 something happens, you start by fixing some epsilon. Now, we know that we know that for epsilon over 2, this is a positive number, there exists an N in N, right, such that for all N greater than or equal to that N, that capital N, A sub N minus L is less than epsilon. Okay, actually, I should correct this. I mean, we know, so we know that there exists an L. Yeah, I need to introduce the limit. So no, we know there exists L in R such that so for epsilon for all epsilon greater than 0, so I'm just going to write it like this. So greater than 0, there exists an N in N such that for all N greater than or equal to N, AN minus L is less than epsilon over 2. If this statement is true for every epsilon greater than 0, it will certainly be true for epsilon over 2. So this is just the definition of convergence anyway. I mean, this is the same thing as adding the epsilon over 2 here. So if it's true for any epsilon, any positive epsilon, it must be true that for epsilon greater than 0, so I could have added here the over 2. It could have been the same. So if this is true, we're going to pick here the same epsilon as here, and we're going to use that to say then that given that epsilon greater than 0, we're going to be able to say that for all N greater than or equal to N, this happens. And so let N be equal to N of epsilon over 2 then, such that for all N comma M greater than or equal to N is, I mean, I'm just adding, so I'm just going to put this in here. It says AN minus L. L is less than epsilon for all values greater than or equal to N. So this is true, I mean epsilon over 2. So then we know we then know. So then, if n, comma m are two natural numbers that are greater than or equal to n, we have that two things hold. So an minus L is less than epsilon over 2, and that the same is true for AM. And AM minus L is also in less than epsilon over 2 in absolute value. Combining these two things using the triangle equality, AN minus AM, we know that this is less than or equal to AN minus L plus L minus AN minus AM. Okay, so, and this is less than epsilon over 2, and this is less than epsilon over 2. So this whole thing is less than epsilon. So we've shown that this is actually true, that we can find a capital N such that whenever we have two numbers, two natural numbers greater than or equal to that capital N, the difference between AN and AM in absolute value is going to be smaller than epsilon. And that's what it means for the sequence to be a Cauchy sequence. Okay, so one thing then, now that we know this, I mean, we can use an intermediate. Maybe we can. Well, it's not use. I mean, we can we can we can state a lemma that we saw. I mean, we knew this was true for convergent sequences already. So we can give this statement here, which as a lemma. This is true. I mean, the Cauchy sequences are bounded. The proof is essentially the same as in the case for convergent sequences. Okay, so this is going to be left for you as an exercise. And we also have the theorem 2.6.4. Cauchy criterion. Sequence converges if and only if it is Cauchy. We already proved one of the implications, and so I'm just gonna leave again the proof for you to as an exercise. So we already covered one implication. We've already seen that the convergent sequence is a Cauchy sequence. For the other direction, we'll use the fact that from this lemma 2.6.3 we know that a Cauchy sequence is bounded. So we know by the Bolzano-Weierstrass theorem that we will have a convergent subsequence. We will know that there's a convergent subsequence. The idea then is to use the Cauchy criterion to show that that's actually the limit. So remember, the Bolzano-Weierstrass theorem tells you that whenever you have a bounded sequence, you there exists a subsequence that is convergent. That limit for the corresponding convergent subsequence that is guaranteed to exist by the Bolzano-Weierstrass theorem. Well, that limit we will call L. This is a perfect candidate for the actual limit of the whole sequence. The idea is, so this is the idea, so one implication, remember, is if and only if it is Cauchy. So convergence implies Cauchy already done. For the other one, set by Bolzano-Weierstrass. Exist a convergent subsequence then. So for this implication, actually, they say be Cauchy, right? So we pick a Cauchy sequence and we want to show that this Cauchy sequence is going to be convergent. So the sketch is that by Bolzano-Weierstrass, since we already know that this sequence is bounded by the previous lemma, there will be a subsequence converging to L, some limit. This is some limit, and we actually want to show that this limit is actually the limit of the whole sequence. And for that, we use the following facts. So you have, I say, a sub m minus a sub nk. So we'll pick any a sub m minus L. This is bounded from above by am minus a sub nk using the triangle inequality plus a sub nk minus L. And this is going to be smaller than, say, some epsilon over 2 because this a sub nk converges to L. And this will be smaller than epsilon over 2 provided m is large enough and n sub k is large enough as well, right? Because it's Cauchy. So this is going to be because a sub n is Cauchy, and this is going to be the case because a sub n sub k is convergent or converges to L. Converges to L. Right, so by definition of convergence, this term, let's start over here, maybe. For this part to be smaller than epsilon over 2, we need to make sure that m and n sub k are both greater than the n provided by the fact that this sequence is Cauchy, which we're assuming. So we just need to make sure that k and m are large enough. Right now, we know that eventually a sub n sub k is going to be close enough to L, just because the sequence is convergent. So what you need to do is to choose nk uh, or k, so large so that n a k as n sub k is greater than or equal to the capital N in the property. I mean, the capital N referred to in the property of first of all the sequence being Cauchy, and also you want k to be so large that this is less than epsilon over 2. So if you pick the maximum between the two, then these two conditions will hold at the same time, and this will be less than epsilon. And that is the proof. So I'll just leave it to complete the details. But the idea is that you need to. I mean, I'm asking you now to start doing things on your own. I can give you some hints in the actual idea, but I want you to start writing down proofs and making these ideas rigorous. That's part of what you have to do when you do mathematics. You need to learn this skill. So I have no problem actually giving you an outline, but you need to be able to complete the details, and this is going to be very useful, and it's going to have a, I mean, if you're able to do all these things and complete them in time, it's going to have a very positive impact on your future studies. So I'm now giving you part of your the responsibility for your development as mathematicians. And of course, if you have questions, I mean, I'm gonna be. I mean, hope I can clarify anything that you may want to. I mean, if you have any questions, just don't hesitate to ask. But I think it's very valuable, even if you don't arrive at the right answer, to try to do this or to complete the details here on your own. So now, now that we've covered this, I mean, there are going to be some problems from section 2.6 that you should work on. And the important thing now is to move on to 2.7. 2.7 is the section or chapter or subsection. Yes, a subsection. Deals with series. Remember that we said at the beginning when we started discussing sequences that our goal was to study series, because series will be studied from the point of view of them being sequences. The partial sums, I mean, the partial sums will be sequences, and so the infinite series will be treated as the potential limit. I mean, when these partial sums are convergent, then the series takes in the value of the actual limit of this these partial sums. Okay. Now, remember what we said before. That so the a series is said to converge to is said to converge if the partial sums converge to a limit, and that limit is the value of the series. So we make sense of the sum of ak from k equals 1 to infinity. We can make sense of that whenever the sequences, I mean that the sequence of the partial sums is convergent, and that limit is the value we assign to this infinite sum. Okay, if in the same definitions and notions of divergence apply here. So if the partial sums don't converge, we say that the sequence of the partial sums diverge, and that's say that the series diverges. Okay. So now, first thing we need to talk about is some elementary It's elementary properties of series. So if those are things that are gonna be so these results are things that you already know, so they're just gonna be a review for some of you, because these things are things that are covered in Calc 1, not in Calc 2, at least here at NMSU. And although you may have not seen the proofs of many of these statements, I always try to give at least a sketch of the proofs of these statements for my students, but none of you were my Calc 2 students, so probably we'll need to go over some of these things, but these are very elementary properties. So k equals 1, the sum from a equals 1 to infinity of c times a sub k is the same as c times a. So just what you would expect, so we can pull the constant out. This is true for any constant c, any real constant c. I mean, in fact, this is actually much more general than this. Remember that what we said before, we have a sequence. I mean, the series are limits of sequences, infinite series. The sequences being the partial sums of the A case and in this case. So because, I mean, whenever you're adding finitely many numbers and you're multiplying all of them by c, you can factor out the c. You can always pull the c outside for the partial sums. And you know, when you have a convergent sequence, any convergent sequence, I mean, it doesn't need to come from a from partial sums. Although you can always write that as a partial sum, but that's besides the point. You can always take outside the constant of a limit when you're computing the limit of a sequence. So c times the sequence, and you can always pull so the limit of c times some a sub n, and you take the limit when n goes to infinity. You can always pull out the constant, and this is actually something you've done before in perhaps not in the same way, or you've not seen it as being a particular case of what we're discussing here, when you computed derivatives or computed limits or the limit loss or stuff like that. So I mean, you just did that for particular sequences, but this is the same thing is at play here. So the second property is that you can add this thing. So this is not, again, just a trivial statement, because so the fact that the series made up of a sub k plus b sub k is equal to a plus b. First of all, because this, what we're writing here on the left may not even be defined. Remember that this is just a notation for the limit of the partial sums. So this may not make sense. So this is actually, some content here is not just simply distributing here and separating the two sums. Okay, so it tells us here that this the sequence of partial sums of the a case plus b case converges to the series for the a case plus the series for the b case. Again, I mean, kind of the same idea is at play here, and just the fact that whenever you have the partial sums, then you can actually split the sum into sum of the a case up to a certain n, and the sum of the b case up to a certain n, and then Of course, each one of these things is approaching a limit, and we can use something again, the triangle inequality, and that will give us the yeah, so that will give us the convergence to A plus B. The second property. Okay, so now proof. I mean, just from here on, I mean, until we finish discussing series, actually, I'll just either skip some of the proofs, or meaning that I will leave them to you to go over at home, because they're basically review, and it's just basically, well, in most cases, the proofs amount to simply looking at the definition and using the same kind of arguments that we've been using, and also because it's kind of a review, because all of these things you already know. Perhaps not all the proofs, but as I said, the proofs are just adaptations of things we've done in the past, and we can move much quicker. We need to hopefully try to get to more interesting stuff, discuss continuity and stuff that is really important. Not dwell too much on series. But okay, so the proof for I. So we know that sum from k equals 1 to n of c times a sub k is equal to, as I said, so maybe we should use a different letter, capital N, c times the sum of the a sub k's. Why is that? I mean, remember, we're only adding finally many terms, so this is just a distributive law. This is just, as I said, this is just a distributive law that we know from elementary school, maybe. Yeah, but this is just because n here is a number, a given number, it's a fixed number. And so we already know that this converges to the sum from k equals 1 to infinity of the a sub k's. Yeah, because I mean, this is what we're assuming, that the sum of the AKs, the series for the AKs converges. Also, this is equal to A. But we're multiplying everything by C, so we just need to show that this times C converges this times, no, to C times A. And this is kind of I mean, this is kind of straightforward. I mean, it's just a matter of writing what we want, so we already know, so that we're going to do it here on the side. Let epsilon be greater than 0. Then we know that there exists some n in n such that for all n greater than or equal to n, a sub n, well, the sum of the a sub k's from k equals 1 to n minus a is less than epsilon, right? So so now so let's try to rewrite this a little bit. So if C is different from 0, this is something we did before, so that's why I'm not dwelling too much in it. So if C is different from 0, we know that this is going to be less than epsilon over the absolute value of C. Epsilon over the absolute value of C. So we should always start again. I mean, I'm not even following my own rule. So you go back here. So the first thing we want to show something, we fix some epsilon greater than 0. So if C is not equal to 0, and again, I'm just um, being more pragmatic at this point here because, as I said, this is something we already know from previous courses, and the arguments are the same. So this is something we already done, and so this is why I'm being more hand wavy at some parts. But I mean, this is actually rigorous what I'm writing now. It's just that I'm um, um, being more casual about writing the proof because I mean this is something you should start now doing yourselves. Because if not, I mean you can just write pages and pages of things. Important thing is you know that this is if C is split in two cases. If C is not equal to 0, which is something we split the case when C is equal to 0 and C is not equal to 0, which is something we did before. When C is not equal to 0, then we know that there's an n such that for n greater than or equal to n, this in absolute value is going to be less than epsilon over the absolute value of C, because this is some positive number, remember? And whenever we have any positive number, then we can find such an n. This is going to be the n associated to epsilon over the absolute value C. And so this implies that if we, again, multiply both sides by the absolute value C, which is a positive number, we can bring this C inside and conclude then that the sum of the AKs from k equals 1 to n minus C times A is less than epsilon, which is what we wanted to show. And of course the case when C is equal to 0 is trivial. Right? So you agree with me then that if instead, so is trivial. Right, because everything here will involve will be 0, so 0 sequence converges to 0, there's nothing really to show. And the second part, the part 2I, is going to be left to you as an exercise, again, which is the same kind of game we've been doing. I mean, using epsilon over 2 instead of epsilon. Yeah, and so we'll continue the next time, but I'm gonna I'm gonna give you a list of things. I'm gonna leave an announcement canvas of things that you or on the module, on the next module, that you need to read. And I'm gonna assume you have read because there are a lot of things here that you already know. And what we really need now is the things we're going to be needing are the actual results, not the actual reasoning. The reasoning you're already familiar with. You're already familiar with this. I mean, we've done plenty of examples of things where we apply these ideas of convergence and using definitions to prove convergence, and also the monotone convergence theorem. So the point here is that you remind yourselves about these results, and how to apply them, not the proofs. Of course, you should go over the proofs, but I'm going to give you a list of things that you should cover about series on your own. You should have plenty of time because there won't be, I mean, there won't be a lecture on Thursday because you have a quiz, so that the time that you should have used for, I mean, there will be an exam, midterm, so the time it will be usually destined to cover material will be used for your midterm. I don't want to take more of your time during a normal. Yeah. So if this had been a normal semester, you would have missed those minutes of lecture. So I don't want to overwhelm you with more material. But even then, I'm still gonna ask you to do some reading, but this is gonna be very light reading. And this is something I do every week anyway. But so, I mean, the idea is that we can move on to more interesting things sooner now than later. There are some things that we're definitely going to skip, so I'm not even going to assign them to you because they're not really that relevant for what we're going to do. But so next week, after you've gone over the things I leave for you to read, we're going to move on to topology, which is a very interesting topic. So this is kind of where the abstract part of the analysis takes place. So we're going to be talking about complex sets and stuff like that. We're going to discuss some things that we did before, and but under a different light. So we're going to talk about open and closed sets. And we're not going to delve too much in neighborhoods. I mean, this is something that you're not really going to be using. But the notion of open and closed sets is going to be very useful. I mean, they're going to be very useful, if only for the notation. Makes everything more clear and transparent when we're writing proofs later on. Okay, so that's all for this week.